Okay, we are at section 21.4, the RLC series circuit. We're going to take what we've learned about the individual devices, the resistor, the capacitor, and the inductor under AC conditions, and we're going to put it all together. So let's share the PowerPoint. Okay, so we have here a series circuit, and you know that whenever there's a series circuit, there's really one current. There's only one current, and that current is I equals I max sine 2 pi f t, or I equals I max sine omega t, where omega equals 2 pi f. So even though we have one current, we're going to have one voltage drop, delta VR across the resistor, delta VL for the inductor, and delta VC for the capacitor. And this is what it's going to look like. It's going to, here's your one current. It's the same current for all, but the delta VR, you can see it's in phase where when it peaks, the resistor peaks, the voltage across the resistor peaks. But let's look at the inductor. The inductor leads the current. The voltage of the inductor leads the current. The voltage on the capacitor lags the current, and this down here, delta V, is the overall voltage, and it's the sum of all three of these. So it's got some phase angle relative to the current. So there it is. Delta V is equal to VR plus VC plus VL. And this is the phase current. Delta V is delta V max times some phase angle, and you can see how it's the cosine. If you look at delta V max and you look at the cosine, I'm sorry, it's the sine. It's opposite. It's not the adjacent. It's opposite. So delta V equals delta V max sine 2 pi f t, or omega t, plus the phase angle, some phase angle. So that's how you get it. I equals I max sine 2 pi f t, or sine omega t. And this is how you determine the phase angle. These are phasors. So you have the, this is what we call the real part is going to be your horizontal, your X, and your delta VL is your positive Y. There's a positive imaginary axis, and delta VC is the negative imaginary axis. And so you add those. You add delta VL and delta VC. Of course, since it's in the negative, you're going to end up with delta VL minus delta VC, and delta VR. You take the square root of the sum of the squares of those two, the delta VR and the delta VL minus delta VC, to get your V max. So V max is equal to delta VR squared plus the quantity delta VL minus delta VC squared. Now the theta, it's the tangent of theta is equal to the opposite over the adjacent. So the tangent of theta is equal to delta VL minus delta VC divided by delta VR. So theta, the phase angle, is equal to the arc tangent, or tangent minus 1, of delta VL minus delta VC divided by delta VR. Now there you got a little mnemonic here, Eli the Iceman, to help you remember that in an inductive circuit, the voltage leads the current. E, the EMF, E leads I. And in a capacitive, I leads E. In a capacitive circuit, the current leads the voltage. Eli the Iceman, if that helps you remember, go ahead and use it. Now here is, let's see, we have delta VR, the voltage across the resistor, is equal to I max times R. Delta VL is I max times the inductive reactance, and delta VC equals I max times the capacitive reactance. So delta Vx max is equal to I max times the square root of the R squared plus quantity XL minus X sub C squared. Now that's what we call the impedance. The impedance Z is defined as the square root of R squared plus X sub L minus X sub C quantity squared. And delta V max is equal to I max times Z times the impedance. Now the tangent of theta is equal to X sub L minus X sub C over R. So let me take a break here and let you see, let's see, I think I have Mathematica, and we can see here, we can see that it's phase dependent, it's frequency dependent. So here, if I change this, you can see that the VL is growing and the VC, the VL is the blue, the VC is the red, and the black is the real part, the resistance. And you can see I can make that smaller. I can make it bigger. That's the resistance. It doesn't affect the inductive reactance or the capacitive reactance. I can right now the capacitive reactance is pretty large. I can make it smaller by increasing the capacitance. What do I do to make the inductor smaller? I reduce the size of the inductor. So to reduce the size of the capacitive reactance, I make the capacitor bigger. You see there, it's getting. If I make it smaller, it gets bigger. To decrease the inductor, I make it smaller. Remember that the capacitive reactance is 1 over 2 pi f c. So that's why decreasing it makes it get bigger, increasing it makes it get smaller. And you can see that it's all dependent on the frequency. The frequency is part of it too. So there's just part of the phasor the phasor diagram, and you can see it's dynamic, dependent on the frequency, the inductance, and the capacitance. Okay, let's go back to our PowerPoint. Okay, so these are the components: your R, your C, and your L. R, there's 0 phase angle, 0 degrees. X sub C, there's a minus 90 degree phase angle. X sub L, there's a plus 90 degree phase angle. Now, when you have a R and a C, it's R squared plus XC. It's negative between minus 90 and 0. And if you have purely inductive, it's positive between 0 and 90. And then when you have all three of them, it's negative if X sub C is greater than X sub L, and it's positive if X sub C is less than X sub L. Let's see if you can see the phase angle. Let's go back to the, let's make this smaller, and you can see, oh, there it went positive because X sub C became smaller than X sub L. There it's positive. Let's see, let's make this, there it's positive also. We make it small enough, the phase angle goes negative. Okay. Now, when it's 0, we're gonna learn that that's a condition called resonance, and it's hard to get that right there, but that would be resonance. So let's let's go back to the PowerPoint. Okay, so these are the components, and those are the conditions. If it's purely capacitive, the phase angle is negative. If it's purely inductive, the phase angle is positive. And if it's you have to calculate the x sub L minus x sub C to see if it's positive or negative. If x sub C is greater than x sub L, then it's negative. If x sub C is less than x sub L, then it's positive. Okay, let's go to the next one. These are some problem-solving strategies for RLC circuits. You calculate x sub L and x sub C, and then you calculate the impedance. How do you calculate the impedance? Well, you take x sub L minus x sub C, square it, add it to the R squared, and take the square root of it. That's how you get your impedance. Then you use delta V max equals I max times Z. Now, you might have to find the I max by taking delta V max divided by Z. Then you calculate VR max with I max times R. Delta VL max equals I max times X sub L. And delta VC max equals I max times X sub C. And you can obtain the phase angle from phi equals the arc tangent of X sub L minus X sub C over R. And that ends this 21.4. Next, we're going to talk about power in an AC circuit.